right, so last time we covered the concept of covariance. Covariance is related to the relationship between two random variables defined on the same probability space. Today we'll start by doing two examples using covariance and related concepts. The first one is variance in the hat problem. I'm sure you all remember the hat problem, but let me do a quick review. So there are n people, and they randomly shuffle their hats. Okay, so there are n people, and hats numbered 1 through n. Okay, so each person has a hat that is distinct from all other hats. The hats are shuffled, and the question is, what is the expected number of people who are wearing their own hats after the shuffling operation? And if you remember, we computed this as 1, and it was an example of the use of the indicator function. Okay? So today we'll use the indicator function to analyze the variance of the number of people who are wearing their own hats. So let n be the number of people who get their own hat back randomly after this shuffling. Okay? Who get their own hats back. Okay? So how do we express n in terms of indicator functions? We defined last time the indicator function I sub I as being equal to 1 if person I got their own hat, gets their own hat, and 0 otherwise. Now, these indicator random variables, are they Bernoulli random variables or not? For all I from 1 to n, right, I goes from 1 up to n, are they Bernoulli random variables? Yes, they are. Because they are 1 with probability p, 0 with probability 1 minus p. What is p? P is the probability that I is equal to 1, and it's the same for any I. Why? There's nothing special about person I. By total symmetry, the probability that person I gets their own hats back is, well, there are n possibilities for the hats. By symmetry, the probability that person I gets their own hat back is 1 over n. Okay, because there are n hats and each one is equally likely for person I. Okay. Now, are I sub i's independent of each other? They are not. Why not? Because if person 1 gets their own hat back, now there are n minus 1 choices left for the second person. And person 2 is now more likely to get his own hat back, given that person 1 got his own hat. Now, because the probability, given that person 1 got their own hat, the probability, conditional probability that person 2 gets their own hat becomes 1 over n minus 1. Why? Because one person and one hat is out of the picture. Okay, the problem reduces to a problem of parameterized by n minus 1 rather than n. Okay, so then let's just say, let's try to find the expected value of I sub I times I sub j. This is very important. Okay, this computation is important because it's related to covariance and it tests a lot of probability skills that you've built up. Okay, so let's see. How do we do this? I sub I times I sub j. I sub I and I sub j are either 0 or 1. So the product is 0 whenever any of them is 0. The product is only 1 if they are both 1, right? So this is 1 times the probability that II and ij are both equal to 1. Any problem here? Okay. So, what is the probability that II is 1 and ij is 1? Well, we can break this up using conditional probabilities, right? This is the probability that II is 1 given that I sub j is 1 times the probability that I sub j is 1. Okay? We know this. We already know this. It's p, which is 1 over n if there are n people and n hats. And the other one is the conditional probability that we just talked about. Right? What was that? 1 over n minus 1. Great. So we basically computed the expectation of II times ij when I is not equal to j. Let me just say, this is true when I is not equal to j. I and j are different. Okay? When I and j are the same, then what do we do?
It's 1. 1 plus 1 over n minus 1.
1 plus, that would be was too much.
So it's just 1 over n.
1 over n, right. Because II squared is 1 if and only if II is 1. Okay? And that happens with probability p, which is 1 over n. Okay, great. So we got this. Now let's also compute the covariance. Now we're using the covariance which we defined last time. Covariance of II and ij. You remember what the definition of covariance was. Let me remind you. Covariance of two random variables is the expected value of II minus expected II times ij minus expected ij. So it's just like a variance for two different random variables. If these two were the same random variable, we would get variance here. Right? Covariance reduces to variance when the two random variables are the same. Okay? So this is the definition of covariance. Sometimes the following definition is easier to use, and we proved the equivalence of the two definitions. Expectation of the product, II times ij, minus the product of the expectations. When is this 0? When is this equal to 0? That's 0, for example, when II and ij are independent. In our problem, they're not. They're never independent. But but they could be uncorrelated, even if they're not independent, right? It's still potentially possible that this is 0, right? However, in this problem, we'll find that they are correlated. Let's see. Do you think they are positively correlated or negatively correlated? Good move. I say positively because, again, let me remind you our discussion. If person 1 gets their own hats, this makes it even more likely for person 2 to get their own hats. So they are sort of positively related. Okay. So let's compute what exactly it is. Well, first we need the expectation of the product, which we do have from here. And we have this, yes. We have this as 1 over n, and this is 1 over n. Expected Ij is this. Okay, so I can simply write down this covariance when I is not equal to j and when I is equal to j. When I is not equal to j, I have 1 over n minus 1 minus 1 over n squared. And in the case I is equal to j, I have 1 over n minus 1 over n squared. I think you will remember this one from somewhere. The variance of a Bernoulli random variable, remember, was p minus p squared. Okay, so this is very reassuring. We're probably doing things right. Okay, so let me sort of simplify this expression. Let's see. Or let's not simplify it. Let's leave it as it is for now. Okay, so this is the covariance of II and Ij. So let's return to our problem. Our problem is addressing the variance of n. Okay. So we need to worry about the variance of n. Now, what does n have to do with the i's? I sub i's.
It changes the probability.
N is defined in terms of the I sub i's. How? N is, I'm really expecting you guys to tell me this, the sum of i's. Very nice. Summation of I sub I from 1 to n. Right? This is the whole reason we're using the indicator function, because in this case, I can represent what I'm interested in terms of the indicator functions, which makes life very easy. Okay, so I need the covariance, I need the variance of n. Okay, this is the variance of the sum of i's, I from 1 to n. Okay, let's make a definition. Let's define I tilde as I sub I minus the expectation of I sub I. The reason I do this is to make computation easier in the rest, because in the rest we'll have a lot of, multiplication of summations, etc. Okay. Now, if I do this, let's see. I can then say the variance of the summation of i's is the same as the variance of the summation of I tildes. Why is this true?
Because expectation is a constant.
Right. When I take out a constant, this does not change the variance. Okay? So when I go from summation of i's to summation of I tildes, all I'm doing is subtracting a constant. Okay, and this does not affect the variance. Okay, nice. So the variance of I tildes. What's next? What can I do? Well, use the definition of variance, right? Expected value of this squared minus expectation of the whole thing squared on the outside. Okay, expectation of summation I tildes squared. Right? So we'll now see the benefit of having defined II tildes. What is the expectation of II tilde? 0, because I already took the mean out, and it's a 0 mean random variable. So this is 0. Okay, so I just have to worry about this. Okay. Let's see. Any problems so far? So far, so good. Okay, so let's continue. I need expectation of the square of the sum. Of II tildes. Okay, let's keep the expectation. And let's take the square. Let's expand the square in the inside, okay? This square is, if you want, let's just go slowly and write this as summation I from 1 to n II tilde times summation j from 1 to n ij tilde. Right, no problem. But I can write this in the form of two summations. I would like to collect the I equals j terms in one summation and cross terms in another summation. I can express this as, you know, I from 1 to n II tilde squared plus expected value of the summation I from 1 to n, j from 1 to n, but j is not equal to I. These are the cross terms. Okay? II tilde, ij tilde. Okay? Now, what is this term? Let's think about this term. Expectation and the summation.
İki olmayacak mı bu parantez içinde?
There's no 2 here because, let's see. I already took out the cross terms. So this means, so as I go through all the numbers 1 through n, this also goes through 1 through n, but when this index becomes 1, this goes through 2 to n. When this index becomes 2, it goes through 1 to n, skipping 2. So how many terms do I have here? How many terms? N times n minus 1 terms. Okay, so it has all the combinations in it. But this has n terms. N terms. Yes, please. Okay, it's here. It's II minus its expectation. Expectation is just, in this case, 1 over n. So I take 1 over n out of II. So I just take my random variable and subtract a constant. This makes its mean 0. It doesn't change its variance. Okay? I take my random variable, subtract this constant, which is its mean. Okay? So let's continue. I have here n times the variance, right, of II. Why? Because the expectation of II squared is nothing but also the variance of II tilde, because it's a zero mean random variable, but the variance of II tilde, well, if you want to think of this, you put the definition back in. This is II minus expected II squared, which is by definition the variance of II. We're doing a lot of probabilistic algebra here. Maybe it's a good exercise for all of you. II minus expected II squared. Huh? Right? It's the same as II tilde squared. By definition, when I move the expectation in the summation, the expected value of this term is by definition the variance of II. Okay, let me move on. The next part is more exciting. Okay, so I'll go slowly here. I'll just move the expectation inside the two summations. And I have, again, my terms, I and j. I is not equal to j. Okay. So, tell me this term. It's the, very nice. It's the covariance of II and ij. Because it's the expectation of II minus its mean times ij minus its mean. So this is the covariance of II and ij, which I actually computed. Let me see. So let me just plug in the term, what we computed now. N times the variance of I sub I. What is the variance of I sub I? Do you remember? 1 over n minus 1 over n squared. Right. 1 over n minus 1 over n squared. So I got that. Plus, I have n times n minus 1 terms. All the terms are the same. And they are the covariance of this. I and j are not the same. So the covariance value was equal to 1 over n squared times n minus 1. Let's see. Is that right? Yes. Okay. So, let's just make the easy cancellations. I have 1 minus 1 over n plus 1 over n. And the surprising but nice result follows. It tells us that the variance of n is 1. Okay? So the we just found that the variance of n is 1. So the variance of the number of people getting their own hats is 1. And if you remember, the expectation of n was also 1. We did earlier. Computed earlier. Okay? So, I think this was a nice exercise, as I said, of some probabilistic identities together with the concept of covariance. Any questions? Yes, please. Excuse me? That's the covariance of II tilde ij tilde. Yes, we did. Yes. Any questions?
Biraz karmaşık bir şey de, yani mesela bu I eksi expectation I gibi bir şey tanımlıyoruz falan. Yani böyle, bizden beklenen bir şey mi böyle bir algebraik deha göstermemiz?
I don't know how to answer that. Yes, I think yeah. I would expect that from you. You don't absolutely have to do it this way. Okay, you can keep the expectation of II throughout your computation. This makes the writing sort of more simple. It just simplifies the writing of the derivation, nothing else. There's no new idea here. Okay, you don't have to specifically come up with this idea. There are an unlimited number of ways to solve any probability problem. Okay, you don't even have to come up with indicator functions, except probably otherwise this problem would be difficult to solve. But once you define indicator functions, you can do it in your own way, and provided you do nothing wrong, you do nothing that violates probabilistic identities, you will reach the same answer. Okay, so yes, I believe you guys have all the necessary skills and technical ability to do this, but no, you're not expected to find out, come up with exactly this. Okay. Okay, so let's move on.
Şimdi şu expectation value anlaşılabilir bir şey, yani fiziksel olarak düşünebileceğimiz bir şey yani. Ama variance'ın anlamı ne? Yani biz bir event'i şey olarak anladık.
Variance, so what does variance mean? That's your question? So
hesaplayabiliriz ama ben kafamda oturtamadım, ne olduğunu bilmiyorum hala.
Okay, variance is related to how much a random variable is expected to differ from its mean. But it's a squared difference from the mean. Yeah? So there are a lot of random variables, for example, with mean 1. I can come up with an uncountable infinite number of random variables that have the mean 1. Okay? For example, very simple distribution. It has two probability masses at 1/2 and 3/2 of equal value, 1/2, 1/2. Its mean would be 1. On the other hand, I can come up with something like this. It's equal to -10⁸ with probability 1/2. Okay, so let's break the axis here. It goes up to -10⁸ with probability 1/2, and it's equal to +10⁸ with probability 1/2. In this case, the mean is 0, but you can shift it such that the mean will be 1. Let's say, how do you shift it? Add 1. That's not going to do it. Add 2. Add 2. Add 2 here. How about that? Okay. Or add 1 to this and 1 to this. Okay. The mean of this distribution would be right at 1. Okay. Now, as far as mean is concerned, the mean is also called the first moment. It's a first order statistic. These two things are the same. So it shows you how limited the first order statistic is as a measure. The variance is a second order statistic that distinguishes these two things really well. In this case, the variance of this thing is what? It's 10⁻⁻16, right? It's 10⁻⁻16, roughly. The variance of the other one, 1/4. Okay? So that's what variance is. But variance also doesn't tell you everything. Okay? Sometimes you would need higher order moments, higher order statistics. Okay? So that's it. And so sometimes the square root of variance carries a lot of intuitive understanding. For example, in statistics they use standard deviation a lot when they report some data. When, for example, we announce your exam scores, okay, we usually announce the mean and the standard deviation. and you look at the standard deviation to see how many standard deviations over or below the mean your score is, and that gives you an idea of, you know, perhaps your letter grade. Okay, that's the method that you call, is legendarily called the curve. Okay, so you see, okay. So anyway, let's do the other example, which is very similar, except it talks about, this time, independent Bernoulli random variables. Let's wake up our computer. Okay. So here is the problem. Let x1, x2, x3, and so on be a sequence of IID Bernoulli P random variables. This random sequence is also called a Bernoulli process. For concreteness, suppose that x sub I stands for the result of the ith trial in a sequence of independent trials, such that x sub I is 1 if the trial is a success, and x sub I is 0 if the trial does not result in a success. Okay? The first question is to find the covariance of xi and x sub j for any I and j. Okay? So number 1, find the covariance of x sub I and x sub j. Okay? There are two cases here. When I is equal to j, what is the covariance? When I is j, when I is the same as j, covariance is variance, right? Covariance definition reduces to the definition of variance, and the variance of xi, since it's a Bernoulli random variable, it's p minus p squared. We know that. When I is not equal to j, what do? They are independent. So they are uncorrelated, which means correlation is 0. So it's 0, y, xi and xj are independent. That's given in the question. This means that they are uncorrelated. Okay? Independence implies uncorrelatedness. Uncorrelated, in other words, covariance is 0. Uncorrelated means covariance is 0. The correlation coefficient rho is 0. It doesn't. The implication doesn't go the other way, and we've given examples if you remember. Okay, what's next? Now we define another random variable, another sequence of random variables. So we originally had x1, x2, x3, so on. Now we define for every xi a y sub I, y1, y2, y3. Okay? Yi is defined in the following way. For every I, if trial I is successful, we toss a fair coin. If the coin comes up heads, we let y sub I to be 1. Otherwise, the value of y sub I is set to 0. Okay? Now let's find the covariance of yi and yj, and the covariance of xi and yj for all I and j. Let's see. Let's first think about y sub I and y sub j for different I and j. Y sub I and y sub j are produced from x sub I and x sub j according to an independent process. Okay? completely independent from I to j, we toss a fair coin, provided that given trial was a success, we toss a fair coin. Okay? So yi is 1 if xi is 1 and the coin comes up heads and 0 otherwise. For all I. For all I, 1 up to infinity. Okay. So this implies that yi and yj for different I and j are independent, clearly. Because yi is a function of xi and yj similarly depends on xj and an independent coin toss. Okay? And yi depends on xi and an independent coin toss. So since xi and xj and the coin tosses are independent, yi and yj are independent. Okay, any problem here? So automatically we get that the covariance of yi and yj is 0. If I is not equal to j, that is. Okay? If I is equal to j, it's equal to the variance of yi, which we now need to compute. Let's compute the variance of yi. That's easy from this definition of yi. The variance of yi is the expectation of yi squared minus expected yi squared. Expectation of yi squared. Yi squared is 1 if and only if yi is 1 itself. So yi is 1 when there is a success and the coin comes up heads. We need to multiply the probabilities because these two things are independent. Success probability is p, I guess. And the coin coming up heads is probability 1/2. So p over 2. This is p over 2 minus expected value squared. Well, p over 2 squared, right? Okay. What's next? We need this here. So let's substitute. 0 if I is not equal to j, and it's equal to p over 2, 1 minus p over 2 if I is equal to j. So we got the variance, got the covariance of yi and yj. Now, the next thing is the covariance of xi and yj. Okay? So let's write that down. Covariance of x sub I and y sub j. What do we do? Apply the definition, I guess. So let's use this definition. Expected value of xi yj minus expected xi times expected yj. Right? So, in case that in the case that I and j are the same, can you see that this will be 0? No, in the case when they are the same, they won't be 0. In the case when they're different, xi and yj should be uncorrelated, right? It just makes sense because there is no reason why y sub j should depend on x sub I. But let's see that they are uncorrelated by doing the computation if you want. So let's write here, well, x sub I, y sub j is, this is equal to 1 if both xi is 1 and yj is 1. And it's 0 in all other cases. Okay? Yes, please. Exactly, but there are people who were not convinced that they are independent, so uncorrelated. That's why we are computing it. You know, I think it's a good exercise anyway. So expectation of the product is, well, 1 times the probability that this event occurs times 0 plus 0 times the probability that it doesn't occur. So it's 1 times the probability that xi is 1 and y sub j is 1 minus, this we can just write, expected xi is p, right? And the expected value of yj is p over 2. Okay? So what is the probability that xi is 1 while y sub j is also 1? Now that will be different depending on whether or not I and j are the same. If I and j, so if I and j are the same, then first we need a success, which happens with probability p, and then we need heads to come up, so 1/2. And here we have p squared over 2. If I is not equal to j, well, the probability that xi is 1 is xi is 1 is p, and then for y sub j to be equal to 1, we need xj to be first equal to 1, which happens with probability p independently of x sub I, and then we need the heads to come up. P times 1/2 minus p squared over 2, which is 0. Okay, as expected. Which one? This part? This. Okay. This is the probability that xi is equal to 1. And given that xi is equal to 1, this is the probability that x sub j is equal to 1. Let me repeat. Let me write this over here using a colored marker. Okay? So I would like you to focus on this again. This is the probability that xi is 1 times the probability that y sub j is 1 given xi is 1. Okay? This is p. Now this is the same as the probability that yj is equal to 1 because of independence. Okay? So this is nothing but p times 1/2. Okay? So we have p squared over 2. Okay? So, I mean, we simply use the independence of xi and yj here, which we could have directly used to say the covariance is 0 in the case when I is not equal to j, but, you know, for the sake of exercise, we went through it the long way. Okay. Now, there is one final part left in that question. And I believe that's one of the most interesting parts of that problem. We define another random variable z sub I, for every I. And z sub I works exactly the opposite way from y sub I, such that z sub I is 1 whenever xi is 1 and the coin comes up tails. Find the covariance of y sub I and z sub I for the same I. Well, first of all, for I and j, the covariance of y sub I and z sub j would be 0. That's clear after this much discussion. But what is interesting is the covariance of y sub I and z sub I particularly. What is the sign of the correlation coefficient for y sub I and z sub I? Do you think? Negative, right. Because they work the opposite way. Let's show that that's the case. We need to compute the covariance of y sub I and z sub I. So expected value of yi zi minus expected yi expected zi. This part is easy. Let's write this part first. Expectation of yi we already computed as p over 2. Expected value of zi, p over 2 again because the coin is fair. It's zi is equal to 1 if the coin comes up tails, which is exactly symmetric to the yi case. So p over 2. So we just need this one. What is that? Now, yi times zi is 0 if yi is 1. Because if yi is 1, zi has to be 0. The coin will come up either heads or tails. If yi is 1, it means the coin comes up heads, so zi will be 0. It's 0 if yi is 0, right? Because if yi is 0, the product will be automatically 1. So this product is always 0. So the expectation is then 0. And we have this minus p over 2 times p over 2 term, and this gives us negative p squared over 4, and the covariance of y sub I and z sub I is negative as we expected. They vary in opposite directions. That brings us to the end of this example and to the end of this hour. The topic for next time is transforms or moment generating functions. Okay, I'll see you on Thursday.